All right, welcome back to C69, everyone. So just a quick recap about where we are. So last week, we talked about a user program. So what is a user program, basically? Well, it's the idea of an OS runs program. And who writes those programs? Well, programmers, right? So programmers, they can write a program in C, for example, compile it, and then ask the OS kind of to execute it, right? Either through a command line or through the GUI. So what we saw last week is that those programs, they need to do stuff. So they need, for example, some I/O. They need to get input from the keyboard. They need to print on the screen. They need so I/O, but they also need to create child threads and so on and so forth. So child process and stuff like that. So and by doing that, actually, we introduced the concept of process, the concept of thread, and so on. Right? To do those stuff, well, the programs are not going to do it directly. They're going to talk to the kernel, because the kernel, the OS kernel, is the component that is going to manage all of that. It's going to manage synchronization between the different threads. It's going to enforce protection and so on and so forth, right? And so how does this user program talk to the kernel? Well, they don't talk to the kernel directly. They use something we call system calls, okay? And the idea of a system call is that actually there's some kind of a protection between the user space and the kernel space, and the system call is using interrupt to actually trigger something, trigger a system call to be executed in the kernel mode, right? So we have done that. So then this week, you're starting to work on Pintos, okay? And on project 2. So again, Pintos does not have the concept of a process, and neither doesn't have the concept of user thread, okay? But it has actually a kernel thread, and on this kernel thread, you can run programs, okay? So now in project 2, you have programs that you can actually compile and then give to the Pintos command and then run. So same thing. So these programs, they have access to some to the OS, to the kernel. They're doing system calls, but they are doing it through libraries, right? So, and what I hope by now is you have watched the first video. I gave you about the project. You have looked at the code, you have traced that, you understand how the system call work, you understand how the arguments are pushed to the stack, and so on and so forth, right? So if you haven't done that, you should start working without further delay. So if you have done all of that, you might realize something. So, you can trace system calls, you see how they're executed and so on. And when it comes the time to actually, so by the way, there's no system call implemented in Pintos, right? You have to implement that. There's all the interrupt stuff and so on, but then the kind of system call handler is empty, okay? So you have to implement that. And to implement that, what you have to do is as soon as there is a system call, and you're kind of handling the interrupt, you need to figure it out, okay, what's the system call function and what's the arguments that the current running thread put on its stack, okay? Again, it was pushed on its stack. So you need to read this, you need to know the current thread, you need to look at its stack, and then from its stack, you have to kind of extract the arguments. Okay, so if you have started to work, if you're quite advanced and you have started to work, you might have realized something. It's the addresses, there's something with the memory addresses, because there are some addresses that are what we call user mode address, and there are some addresses that are in kernel mode. Most likely, the ones that have been pushed to the stack for system call, they are user mode, because that's the address that the user program has access to, okay? And when you're in the kernel mode, you are executing actually the system call, you need to somehow to translate that address from the user mode to kernel mode to do something with it, okay? So because of all of that, well, we need to understand how this virtual memory works. And that's going to be my lecture today. We're going to talk about virtual memory, okay? So let's start. So what's the problem with managing the memory? So I'm going to start with a basic idea, which is the following, right? We want to have multiple programs being executed at the same time, okay? And the idea is behind each program, really there's an executable, meaning there's a kernel thread running this program. But each program, has its own stack, maybe its own heap, okay, if needed. But you see, but they all need to be kind of located somewhere in memory, okay? The code has to be located somewhere in memory. The stack has to be located somewhere in memory for each program, okay? So what you can do is like, it's perfectly fine, you can place those programs at random location in memory. It's not a problem as long as you have enough memory, okay? So, here, for example, if I have this memory here, I can place program B and program A, it's fine, okay? But it's not good for two reasons, okay? One is like, we're gonna see that placing programs at random location, it's not that easy, okay? Because of the way we compile and run programs, okay? I'm gonna talk about that. Another one that we keep talking about since the beginning is like, we want the program also to be, to not interfere with each other. And to avoid interfering with each other, it means that program B, for example, should not be able to read or write the memory that has been reserved for A, for example, okay? Because otherwise, B is going to be able to kind of mess up with the data of A, okay? So we want also to isolate that. And the answer for these two programs is going to be virtual memory. But before, let me kind of recap about what's happening when you compile a program, okay? So, let's go back to B09, you learn C, or even you learn C in A48 now. And when you compile a C program, you can do it in one command line, okay? But most of the time, what we teach actually is like to do it in two steps. And these two steps correspond to first the compiler and then the linker, okay? So what's that? The compiler basically takes the source, okay, and is going to transform it into something that is not really machine code directly, okay, but it's something kind of in between, okay, and we call that usually the object file, okay. Usually when you compile, we say, we compile a program.c and we turn it into a .o. Once we have this object file, okay, we need to link it, and there is a second step, okay, and when we link it, actually, we take this object file and we turn it into a binary, okay, and a binary is really something that we can run. It's it's directly executable by the CPU, okay? And what's this linker doing? It takes this object file, which has actually symbolic addresses and so on, and turns it into absolute address, okay? So meaning kind of like static address, okay? So again, maybe you're used to actually compile C program in one line, okay? You can do this kind of thing in one line, but again, what's happening behind the scenes, it's these two steps, compiling, linking. So something that you can do if you're interested, you can actually compile the C program into a binary, and then you can decompile the binary, okay? What's decompiling? You can turn the binary into assembly code. Again, it's an assembly code that is understandable by us, right? I mean, programmers, right? But again, the binary is just like a series of bits, and those bits are instructions, okay? But decompiling is like putting kind of a word behind bits. So if we do that, okay, but in a way here, it's not decompiling, so it's called disassembling. Okay, decompiling is something else. It's disassembling. If we do this this exercise, we're going to realize the following: when we disassemble the binary, we see instructions. So instructions x86 instruction directly executable by the CPU, and those instructions, those instructions, what they do is like, of course, it's like, the basic stuff that you have probably seen in B58, which is, there is a bunch of instructions to do some arithmetics, okay? There are some instructions to do bitwise operations. There are some instructions to read and write to memory, okay? And there are some instructions to call functions and other instructions to basically do jumps, right, in the code. And with those jumps, actually, that's how behind the scene, loops and if conditions and so on are implemented, because there is no if conditions in assembly. Okay, you have seen that in B58. If you look at these operations, something that you realize is that the memory. So when you do a jump, for example, let me look at an example here. That's the main program. Okay. And the CPU doesn't know main. It doesn't know what's this string about. What it knows is like it calls, and then it calls a function that is located at a very precise memory location. 80484B. Okay, the fact that it's function foo here, this is actually for us. The CPU doesn't know about it and doesn't care. So here it means that the CPU is gonna change its instruction pointer, do something with the stack. Actually, this sub, push, and so on. That's the stack. Okay, you see the ESP here, the stack pointer, and so on. And then here, by executing this instruction call, it's going to change the instruction pointer and then go here at this memory location and then start executing those instructions. Okay, same thing when you return, it returns, it reads the value where it were on the stack, and then goes back here and then execute the memory. Okay, this is a stack-based execution that you have seen in B58. So here, there's surely something that strike you, which is like when we do the compilation and the linking, okay, we do that statically, meaning here, and that's what it says, when you link, you turn, those logical address into absolute address. Meaning when you put this program, when you want to execute this program in memory, when you execute the binary, you need to put this piece of code here at this precise location. Otherwise, it's not going to work, right? I mean, when the CPU is going to say, code blah blah blah, it's if it doesn't find the instruction or if you find something else, it's not going to work. So you see here, we don't have much choice, right? When we execute when you compile a program, okay, the binary has to be, when you execute, it has to be placed at the exact memory location to work. Okay, so it's kind of like it contradicts what I just say here, which is like, oh, fine, you can have programs, you can place them in random location in memory. Well, no, you cannot, right? And you could, if, for example, you say, okay, oh, I'm going to compile this program and this program is going to run here. This other program, I'm going to compile it and then run it exactly here. But that's not how it works. And what if program A and program B are instances of the same program? Also, when you compile, you don't know all the other programs that you're going to run on your OS at the same time. It's insane. Okay, so we have a problem. It doesn't work. So here, this is kind of the problem that we're trying to figure it out here. Since function addresses and order are hard encoded in the binary, okay, they are absolute addresses, the program cannot be placed at random location. So how do we fix that? Let's have a naive approach, okay? And this approach actually was kind of attempted in the past, right? The idea would be the following. How about, when we are about to execute the program, we actually really, we change all the addresses and kind of shift them to kind of, put the entire program in some kind of location, right? Why not? Okay. So here, the idea is like, we're going to do kind of the linking because it's kind of like keeping the address in some kind of symbolic format. And then when you execute, actually, this is where, depending where it's going to be located in memory, you're going to turn it into absolute address. Okay. So do this idea of like, turning the logical address to absolute address only when you're going to run it. Okay. So basically, you see where you have space in memory when you run, and then you adjust all the reference in the program. Okay. The problem with that is like, what if, during the program, you need to somehow relocate the program. Okay. And that happens a lot, actually. You will see why later. It's going to be complicated. Maybe it's not complicated for the executable, but now once the program has started to run, you have pointers, you have stack. You have the stack and you have pointers and you have all this stuff. So you need to change all these pointers and so on if you want to relocate things in memory. Okay, so actually here it's going to be very complicated, and maybe this approach actually doesn't make it really that you can actually relocate stuff. Also, you need to find a big free region, a contiguous memory, right? So at first, you have the executable, you have the stack. The stack is going to grow, right? So you need to keep an entire region, even if this region is not used, of contiguous free memory. Okay, so that's kind of a waste of space. And then, we haven't solved the problem of how do we avoid programs interfering with each other. Okay, still, a program can write, an address here that is outside of its scope, and then messing up with a part of memory that is actually used by another program. Okay, so all of that is not very very practical. So sharing the physical memory is not going to be it's not going to be doable. Okay, for many reasons. Okay, so here instead we're going to switch to something we call the virtual memory. Okay, and why are we doing all that? Well, because first, when we have a program, it shouldn't require particular physical memory bits, right? It should be kind of independent, and we should be able to kind of like put this program wherever you want. Okay. Often a program requires a large amount of contiguous memory. Okay, for example, the stack has to be contiguous. If you have a large data structures like an array, the array has to be contiguous, because the way we access it, usually it's like, we have a pointer to the array and then some kind of an index, some kind of an offset to actually access, the nth element in the index. So it has to be contiguous. Also, when you write a program, you're kind of, you as the programmer, you're kind of going to assume that, you have enough memory. Okay, so it's fine. Your machine has 8 gigabytes of RAM. You're going to say, okay, fine, I'm going to write a program that uses 8 gigabytes of RAM, regardless of, how much RAM the kernel needs, how much RAM the other program needs, and so on and so forth. Okay. As a consequence, actually, you can check with your operating system. Most likely, okay, if you are running a lot of programs at the same time, the sum of all the memory used by all of your process is usually greater than the physical memory. Okay, unless you have a huge amount of RAM, but even that, you can run more programs. You can run programs that use more memory than you have physically. Okay, why is that possible? Well, you will see. It's thanks to actually a virtual memory and swapping. We need also protection. Okay, we want to know when a program A runs, if this program goes crazy, whatever, and so on, it should not interfere with B. Okay, and what I mean by interfere, it should not even read from B. Okay, because that would be a problem. Actually, it's a real security problem. Imagine you have a program that look at another program and read passwords or stuff like that. That would be bad, right? Because all this stuff are in memory. And then we want to avoid actually by interfering, also corrupting the memory, right? You don't want the program A to basically write into the space of used by B and then derail B, because every time you have a program that goes wrong, maybe the other programs are going to crash as well. That's not something we want. Okay, so because of all of that, this is what motivates us using the virtual memory. So what can be the goal of the virtual memory? We need to provide a convenient abstraction for the programming for the programmer, right? And the best would be that the programmer writes a program, can do the linking and so on. Can do all the stuff and kind of see the memory as if other programs do not exist, and as if the program can use the entire memory. Okay, so that's actually would be great. And then it's going to be the job of the OS underneath to actually managing all of that behind the scenes, but without the programmer actually taking care of that. Okay, so that's why. So you want to allow a program to see more memory than exists as well, right? Here you can even have a program that uses maybe 16 gigs of memory, even if you have 8. Okay, as long as it doesn't need all this memory at the same time. We will see that in swapping. At the same time, a computer is about allocating scarce resources, and we're going to have competing programs and so on. And basically here, what I mean is we don't want to have managing this virtual memory should not be an overhead. Okay, it should be transparent, it should be quick, it should be it shouldn't be an overhead. Otherwise, if managing virtual memory becomes an overhead, well, certainly our system is going to have bad performances. Okay, and of course we want the virtual memory to kind of enforce protection. Okay, we don't want processes to interfere with each other. Okay, so it sounds like magic, but virtual memory is going to do exactly that. So some definition. When programs interfere, when program read and write from memory, they are going to use virtual addresses. They will never use physical addresses. And here, but when I say program, it's even the kernel. Even the kernel here is going to use virtual memory. Everything is going to use a virtual memory. Okay. Nobody will have access to the physical address. But now, actually, when the CPU executes, of course, the CPU needs to kind of send a signal to the right, to the memory bus and so on. I mean, it needs to know the real address, okay? Because at the end of the day, there's going to be something physical, there's going to be a physical memory. The physical memory has physical addresses, and the CPU needs to talk to the physical memory, okay? There is no such a thing as a cloud memory or whatever, okay? So for that, there's going to be something called the MMU, Memory Management Unit. This MMU is going to be a hardware support that is going to do the translation from a virtual address to a physical address. Okay, and we're going to see how this translation works. Okay, but basically here, the CPU, is going to execute instructions. All the instructions are going to be virtual address, and as it executes, it's going to kind of ask the MMU to translate that very quickly, and then to actually have the physical address. That's in a nutshell what's going to happen. Okay. We're going to see that. Okay. So the CPU, to talk to the MMU, to talk about how to translate and so on. We're going to see those stuff. It has special instructions to actually configure the MMU and so on and so forth. Okay. This is like privileged instructions. Of course, user programs do not have access to those instructions. Okay, it's only going to be privileged, meaning at the OS level. Okay, I said that already. It's going to translate from virtual to physical address, and it's going to give a per process view of memory. Again, when the process is going to run, it's going to be able to use virtual addresses that are in its virtual space, okay, or its virtual address space, and that's it. And it's going to be impossible for this process to actually access others' process memory. Okay. So what's the virtual memory in a nutshell? Again, the application does not see physical memory. It only, talks into virtual addresses. And those virtual addresses, for example, here, imagine there is a load on 30408. Okay. Well, when the CPU executes that instruction, automatically it knows that this is an address because of the instruction format, right? And it's going to kind of give it to the MMU, and the MMU is going to translate it into, first of all, it's going to say, is this address legal? That's interesting, right? It's going to say, okay, is the program allowed to actually use this address? Okay, we're going to see how this is done. It's done through the table. And if yes, it's going to say, okay, fine. The address is actually, the physical address is 92408. Okay, and the CPU is going to use that address actually to talk to physical memory. But again, from the program perspective, you never handle physical addresses. This is all kind of translated at execution time. Okay, so the MMU does this translation. So of course, we're going to need to tell the MMU how the translation work, right? Because again, this is going to be different for each program. I mean, here, for example, this is something important, right? This address 30408 can be used by 6 different threads. Why not? Okay, 6 different threads can use that memory. But again, it's going to be translated to different physical addresses here, depending on which one is executed. So you understand here that the MMU, depending on which program is currently executing, is going to have a different translation. Okay, and it's going to use actually a different translation table. Okay, it will have a table for each process. Okay, process or thread, or I don't want to confuse here, but here, if we talk in Pintos, it's going to be kernel threads. Okay. Okay. If the address is not legal, because somehow it's like it's not in the table. You will see, but it's not in the table, or it's an address that has not been allocated in the virtual address space, it's going to say there's going to be a fault. And that fault, you have seen it many times. It's usually called, so on Pintos, they call it a page fault. Okay, page fault means exactly that. You are trying to access an address that you are not supposed to access. Okay, so you have a page fault. Or if you are actually on Linux and C and so on, well, you have seen probably a segmentation fault. And segmentation fault means exactly the same thing. Okay, segmentation is the old name, and we kept the old name. But segmentation fault means basically that, hey, wait a second, you're trying to access an address that is not in the virtual address space, okay? Meaning you shouldn't access this address, okay? And why do you have that, by the way? Well, either it's a wrong pointer manipulation, or, well, some kind of data has been corrupted and contains, basically a bad pointer, okay? And in Pintos, that's usually a synchronization issue. So that's what's going to happen. So what are the advantages of virtual memory? Is that now actually you can relocate the process while you run, right? Because the only thing it takes, now it doesn't matter where it is in physical memory. If you want to relocate the program, you just need to change the translation table, okay? That's it. And so you can actually completely relocate the program like that. And we're going to do that actually in project 3. We're going to implement something called swapping, and we're going to be able to do exactly that, okay? Why do we relocate? Because actually sometimes we're going to take the running program, offload it to the disk, okay, to free up some memory. And then when we resume that program, we need to bring it back from the disk and put it back in memory, but not necessarily in the same place, okay? That's why we need to kind of relocate. Okay, so there are different techniques for implementing virtual memory, okay? And I'm going to start, with the first one that was proposed, which is called basic address translation, okay? Then I'm going to move to segmentation. That's kind of still an old way, but, systems in maybe like 20 years ago, 20, 30 years ago, they were working using segmentation. But those days, we use something called paging, because paging is actually a better way to do that, okay? So that's why I'm going to introduce them all, 3, but I'm going to spend, of course, a lot of time on paging, okay? Because Pintos use paging, of course. Pintos, all the modern OSs use paging. So actually, I'm going to have another set of slides just talking about paging in detail. But for now, let's have an overview of these 3 techniques. So I'll start with the first one, because that's the naive approach, and it's kind of a good way to understand what's going on. So it's called basic translation, address translation. So you can imagine the following. So again, what are we trying to do? We have a virtual address, and we're going to have the MMU that is going to translate from this virtual address to a physical address. So how will the translation work? Here's the first approach. Imagine the following. We have 2 special registers called the base and the bound, okay? And every time there is like a load, store, or a jump, every time there is an instruction that use a virtual address, okay, we need to translate it. And how are we going to translate it? Well, it's simple. You take the virtual address and you are just going to add the base. And the base here is going to be added to this address. And that's going to give us the physical address. Okay, so you see, very simple. Okay? That means something. If you're following, you might understand right now that, each process, we have a different base and bound. Okay? And so every time you do context switching, okay, remember context switching, like we switch between threads. So when you switch the thread, we also need to switch this base address, right? So so now you can imagine in your TCB, in your thread control block, okay, for example in Pintos, you can actually register what's the base address for that thread, okay? And when you do context switch, you change the base register here. And automatically, again, this is automatic at the hardware level. You don't have to do it at the code, right? And the OS doesn't have to do it neither. It's automatic. The architecture has been built like that. The CPU sees a virtual address, is going to read the base register, and then, the CPU, the MMU, and then that's the physical address, okay? They are also going to check whether the address that you have is, within some kind of boundary, right? This is why there is a bound. Also, the address needs to be between 0 and the bound. Okay, the bound is kind of some kind of a limit, right? If it's not, you trap the kernel, meaning you raise an interrupt that says something like memory. I don't know how you can call it, but it's the equivalent of page fault or segmentation fault. But here we call it like whatever, memory fault. Okay, and then a handler takes over and then do something. Maybe actually kill the thread. Okay, that's usually what you do. So again, it's going to be the job of the OS to actually change these registers when when you do context switch, basically. Okay. And yeah, you need to reload the base and the register and so on. Okay. And of course, if you want to relocate program in memory, you just need to change those base and bound. Okay. Very simple approach. Now, what's the pros and cons of this approach, right? I mean, again, I told you it's not actually what we use in our system because it has some disadvantage. What are those disadvantages? Okay, first of all, advantage, it's cheap in terms of hardware, very cheap. You only need 2 registers to store the base and the bound at any point in time. That's it. Okay. It's cheap in terms of cycle. Okay, adding and comparing it can be done in parallel. Okay, you can actually, I mean, here I'm saying this can be done inside a hardware in 1 cycle, basically. Okay, or a few cycles. So it's kind of very fast. Just adding and comparing. It's actually something we know how to do very quickly. Disadvantage is the following, right? So you understand the following. I mean, if you have a program running like that, so that's the old figure I have where you have the code, you have the static data, you have the heap, and then maybe in this process, you have multiple user thread, and because of the user thread, you have multiple stacks and so on and so forth. So it means here you can have a base and a bound, okay, but you need to allocate a big chunk of memory. Right? You cannot be selective, right? You have a base and a bound, and in the middle, maybe you need to allocate a lot of free space to actually grow, right? But you don't have the choice. Everything from the base to the bound will be allocated. Will be dedicated only to that process. Okay, so here, growing a process is expensive because you need to move the base or the bound and so on, and it's going to be messy, and also it's not a good way to manage free space. Okay. Also, you have no way to share the code or data. Imagine for some reason, you have process A and process B. They want to share data. Okay, or let's say, somehow they need to access the same file and so on and so forth. Right. We have that, for example, when we have IPCs and so on and so forth. Okay, you cannot do it directly in memory. Okay, is it a bad thing? Actually, no, because you can always have system calls to do that and so on and so forth. But okay, the bottom line is that you cannot do it. Okay, I mean, if you have this thing, we're going to see later on with paging, this is actually more flexible. Okay, so what's the solution? And I mean, that was the naive approach. What came up after that is something we call segmentation. That is a little bit better than that. Okay, and the idea here with segmentation, we're going to separate actually within a process. We're going to even have smaller segments. We're going to have one memory segment for the stack, one memory segment for the heap, one memory segment for the code, and so on and so forth. And like this, we only going to if you need to grow the stack, we can just allocate more segment here, right? But you don't need to have like one big chunk. So instead of one big chunk, we're going to have smaller chunks. Okay, that's segmentation. So segmentation, how does it work? The idea is the following, right? Okay, we have our program. That's kind of like, virtually what the programmer sees. The programmer sees, the code here. He knows that the stack is somewhere here at some virtual addresses. The data is somewhere here, and so on and so forth. But then, each process has a collection of multiple base and bound registers in a way. And, each process, we have segments in memory. Okay, so you can think about it as, it's kind of like, you take the idea I had before, but you turn it into like, a multiple segment thing. So here, it's going to say, okay, for the stack of this program, I'm going to have a base and a bound here, or actually here, sorry, here. Okay, for the code here, I'm going to have a base and a bound here. So now actually, when you run a program, you don't have only one base and a bound, you have a collection of base and bounds, a collection because it's all the segments that have been allocated for that program. Okay, and we're going to call that actually a segmentation table. Okay, so now when you run one program, one specific program, it has a collection of chunks, and so it's a collection of base and bounds. Okay, so now it's great because you can actually. Let me talk first about protecting memory as a segment granularity. So I mean, it's better in terms of free space. You're going to see, but now you can even share, right? Because now you can say, okay. Imagine here we have a data that is shared between 2 processes. Okay, here you can have this base and bound being shared. I mean, Shared means it's going to appear in two segmentation tables, one for program A, for example, and one for program B. And like that, they can actually share the same table. And it can be different address, by the way. It can be completely different address in virtual memory, but because it's going to be mapped to the same segment, it's going to be the same data. And here, this is powerful, right? So now they can actually use the same memory, but still without interfering. I mean, they can interfere, of course, at the buffer level, for example, okay, the heap, but not, this program, I mean, another program would not be able to mess up with the stack of program B, and so on and so forth, right? So this granularity is a good thing. Okay, so what are first, let's go to the mechanics, okay? So it's the same as before. Okay, you're going to have a MMU. The MMU is going to being given virtual addresses, and we need to translate it. But this time, to translate, there is no one base and bound. We're going to have a table. Okay. So how is the MMU going to use this table? Well, it works like that actually. So when you have a virtual address, so a virtual address is 32 bits. Okay, in the 32-bit architecture. Okay, 32 bits. So here, what we can do is the following. We're going to consider that, okay, so we're going to take the first few bits, okay, we call it like the strong bits, and we're going to say, okay, the first one are actually the segment index, okay. So you see that's going to be interesting, and then the second part of the virtual address is going to be the offset. So basically here, you have an address, you cut it in two, and you can say one part is the offset. One part is some kind of an index, okay, a segment index, and the other one is going to be the offset. And the MMU is going to do that, right? The MMU is going to read that. And how is going to use a segment? Well, the segment is going to, so the MMU has a pointer to a table, okay? And this table has a bunch of segments. And for each segment, I told you, right, there's a base and a bound. So how do we know which base and bound to use? Well, it's going to take the segment, it's going to turn it into an index. So here, for example, it's 3, okay? So it knows that 3 is going to be 0, 1, 2, 3. 3, here's the segment entry, okay, in the table. And so from that, the MU knows, okay, fine, I got the entry, now I have the base and the bound. So let me check. How do I check? Same thing as before, okay? I take first of all, I take the base and I add it to the address. Okay, so I add the base to the address. I check that the bound is actually it's within the bound. Okay, and I add the base and so on. I check the bound, and if so, this is going to give me the address in the physical memory. Okay, and in the physical memory, it might be something else here. Okay, but there's going to be a segment here, and there's going to be an offset here, of course, 128 from this address here, which is this is actually the segment plus the base. Okay, so that's kind of the math that is happening. Again, this is important, right? What do you manage? You as the OS designer, what do you manage? Well, nothing. I mean, almost nothing, right? You just need to actually create the right table here, and then the MMU is going to do it right automatically. Of course, you need to tell the MMU, here's where is the table, right? Here's the location of the table. And for that, there are some registers called CS, DS, SS, ES, and so on. I mean, there are multiple registers. And you can basically tell, okay, here is where the table is. Okay, so that's called segmentation. You will see, if you understand segmentation, paging is very similar. So what are the trade-off of segment? Segment is very flexible, okay? Because, you need 4 kilobytes of memory, you allocate 4 kilobytes of memory. You need 20 megabytes of memory, you allocate 20 megabytes of memory in one chunk, okay? You just need a base and a bound, and, you update your segment table, that's it, okay? So it's good because now you have multiple segments per process. In a way, this is a sparse memory, right? The rest of the memory is still free, so you can allocate it if needed, right? You can easily share memory, okay? I talked about that. And then, if you don't need pieces of memory, you can actually swap it, and you can swap it. Now you can be selective, right? Maybe say, oh, I don't need the heap, I'm going to swap the heap. back to the disk, right? Or I don't need that, I'm going to swap it, and so on and so forth. Okay. What are the disadvantages? Okay, so it requires a translation. This actually is going to be true even for paging, right? The fact that you need to go in the table and so on, find the right place in the table, and then do the math and so on and so forth, right? So there is a translation. It's going to be the same problem for paging, but we're going to fix it. Okay, no worry. So that's not a problem. The real disadvantage, okay, why actually segmentation is no longer used those days, is because it makes external fragmentation a real problem. So let me explain here. What is fragmentation? You might have this kind of intuition here, right? Again, an OS is something live. Okay, it's live in the sense that you start a process, you stop a process, you start another process, you stop another that process, and so on and so forth, right? So as you start and stop process, of course you need to allocate stuff in memory and so on and so forth. At some point, if you do that for quite a long period of time and so on, maybe at first you say, okay, I'm going to allocate the code here, and then the stack, and then the heap, everything contiguous. But then you're going to start to free some stuff and so on, allocate, and what's going to happen is, like, after a while, your memory might look like Swiss cheese. Okay, so I don't know if you're familiar with the Swiss cheese, but that means that you're going to have a lot of small chunks of free memory here and there, right? Exactly like here. But so we call that fragmentation. It's fragmented. And the problem with that is, like, when we allocate a segment, it has to be a contiguous segment, right? So maybe at some point there's going to be a way that, a situation when you need to allocate a segment and you don't have a free chunk big enough to basically allocate this segment. Okay, although altogether you might have free memory, right? If you do this plus this plus this plus this plus this, you might have free memory. Okay, so of course you might say the following, right? How about where we actually shift stuff and relocate? Yes, you can do that dynamically. You can actually we call that defragment the memory in a way, right? But it's complicated because if you have pointers and so on, if this is a stack and you have pointers, it's complicated. Very complicated. Okay, so you might be able to relocate some stuff, but not others. Programs, for example, are going to be hard to relocate, maybe, and so on and so forth, right? So it's not always easy. So again, so what fragmentation? It's basically, when it's becoming bad, it's the inability to use frame memory. Okay, so over time you have external fragmentation. That's true with segmentations. Okay, so because the segments are of variable size pieces, you might have many small holes. You can have also something called an internal fragmentation. And actually here, the internal fragmentation does not happen with segmentation. Because in segmentation, when you did, or maybe a bit with the stack and so on, but not much. When you need a segment, you need a 20 megabyte segment, you allocate a 20 megabyte segment. If you need to allocate 2 kilobytes, you allocate 2 kilobytes, okay? Because what's internal fragmentation is, like, you allocate a piece, but within that piece, you have some free space. Okay. Might look weird here, but you will see. I'm going to explain paging now, and you will see that if one problem of segmentation is actually external fragmentation, paging is going to solve this external fragmentation. But with paging, we're going to have a little bit of internal fragmentation. But still, it's better to have a little bit of internal fragmentation as opposed to big external fragmentation. So that's why paging is going to be a bit better. Okay, that's a spoiler alert. I'm going to explain paging. Okay, but right now, if I want to finish the part on segmentation, one of the drawback is this external fragmentation. These kind of like a small holes here, and that's a problem. Okay, so that's why because of that we use paging those days. Okay. And so this is what I'm going to spend a lot of time. So I'm going to spend actually the entire second hour of this lecture. This is what Pintos use. This is what Linux, Windows, and Mac are using. Okay, and Unix. So what is paging exactly? So again, at first, segmentation was a good thing. We used segmentation for a while, but then at some point we switched to paging because of fragmentation. So what's the idea? The idea of paging, it's kind of the same idea of fragmentation, except that now we're going to divide the memory into fixed size pages. Okay, and here actually I can tell you usually the value is going to be 4 kilobytes, so it's going to be fixed. And why it's going to be fixed pages? Because we're going to eliminate external fragmentation. Okay, so each process has a collection of maps from a virtual page to a physical page. Okay, and here, for example, you can have, if you divide the memory into pages, so you can say, okay, that's page 0, okay, page 1, page 2, page 3, each of them are fixed size, and so page n. And so you can do the same kind of like, the virtual memory is like that. This is logical, but of course, the physical memory is also divided. And then you can just have a table that says, oh, if you're trying to access a virtual address that is inside page n, it corresponds to page 7 in the physical memory. And like that, we're going to do a translation again. Okay, but now it's kind of fixed. So here, we're going to be able to actually protect and share at the page level, not at the segment level. It's going to be at the page level. Okay. You will see it's weird, but let me explain. So of course, for example, imagine you need a big array. Okay. For example, here you have some data heap. Of course, the array might be bigger than a page. Well, it doesn't matter. When you're going to allocate, for example, here, you're going to allocate 2 pages. Okay. And same thing for the stack. Here, for example, I'm going to allocate 3 pages for the stack. Okay. It's going to be fixed. I cannot, allocate the exact amount. Okay. I'm going to allocate 3 pages. So in a way, I'm going to eliminate external fragmentation. Why? Because even if I free reallocate and free and reallocate and free and reallocate and so on, I'm always going to allocate in 3 pages. Okay, meaning I'm always going to have pages, chunk of pages allocated. And actually, I can tell you the following. Here, this drawing is kind of a little bit misleading because why? Because here, actually, the heap can be allocated. I can allocate 1 piece here and 1 piece there, or the stack can be 1 page here, 1 page here, 1 page here. It doesn't matter, actually. Okay, you will see. So it completely eliminates external fragmentation. But of course, we have a little bit of internal fragmentation. Okay, here, for example, when we allocate that, we might not use that free space in the page. It doesn't matter, it's lost. Okay, actually, there's no perfect solution, but here, this is a very good trade-off. And of course, the average internal fragmentation is going to be half a page. Okay, and so it's going to be 0.5 of a page per segment. Okay, what I call a segment is like a big chunk of data. Okay, at least I'm going to have only 0.5 per page fragmentation in average, and that's an average of 2 kilobytes. When you have a 4 kilobytes page of 2 kilobytes per segment, and that's actually a good trade-off. Okay, so that's what we're using right now. And why paging is better? Well, because there's no internal fragmentation. So you see here with segmentation, the more you leave your OS running, the less it will have memory. So at some point you need to almost like restart the computer to actually make things better. Here, you can let it run the way you want. There is no external fragmentation, so it's always good. Here's a question. What's the difference between a page and a segment? Okay, so I told you a segment, the idea of a segment is like, let me go back. The idea of a segment, for example, is like, you need a segment for the code. Okay, imagine you are running a 6 kilobyte program. You need a segment of 6 kilobytes to store the code. You need a 20 megabytes buffer. You need to allocate a 20 megabyte segment for that buffer, and so on and so forth, right? So at the segment, the segment is kind of like what you want to allocate in the program. But a page is different. A page here is just a fixed size. We don't care about what's going to run and so on. We are going to divide the memory into pages of fixed size. Okay, for example, 4 kilobytes. And then when we allocate a stack, for example, we're going to say, oh, wait, I need to allocate, okay, for example, I need to allocate 6 kilobytes for the stack segment. Okay, well, okay, I don't have the choice. I need to allocate 2 pages, for example, okay? 2 pages is going to be 8 kilobytes, but, I always allocate into chunks of pages. Okay. And then why would internal fragmentation happen? Well, exactly what I explained, right? Imagine, you have a data here that is 6 kilobytes. I need 6 kilobytes of memory. I'm going to allocate 2 pages, okay? And if my page are 4 kilobytes, I'm going to allocate 8 kilobytes, regardless, okay? So I'm going to allocate 8 kilobytes, and that's it. So here, there's going to be 2 kilobytes that are not going to be used, but it doesn't matter. Okay, and I cannot use it. It's going to be, it's gone. Okay, as soon as I look at the page, I allocate it in one chunk. Is that clear?
But why not? If I have a variable that requires 2 kilobytes, why wouldn't I use that piece of the page that is left to allocate that 2 kilobyte variable?
So okay, so there is a difference here. For example, when you do the stack. Okay, I mean, when I say here the heap, right, you could actually allocate 2 pages and then store maybe two arrays. You can do that, of course, right? Okay, that's something, and I'm going to say that actually for Pintos, because I've seen it a lot, students do that. You don't need to, every time you need to allocate something on the heap, I mean, especially the heap, right? You don't need to allocate 1 page per variable. Okay, you're going to allocate a chunk of heap, and then you're going to store all the variables that you want there. Okay, so, but it's going to be per program. That's what I'm saying, right? So, I mean, the heap here can contain multiple variables. That's fine. Okay, the stack, for example, contains multiple variables, right? When you allocate, when you allocate stuff on the stack, you declare variable A, variable B, variable C, and so on. This is all going to go in the stack, right? But what I'm saying is like, when you allocate space for the stack, or when you allocate space for the heap, and so on and so forth, well, you need to allocate a certain chunk. Again, I mean, this is going to be new for you guys. When you write in BO9, you don't care about that. In BO9, what did you use? For the stack, it's automatic. Okay, you write your program, you compile, the compiler is going to figure it out how much stack it needs. When you allocate on the heap, you use malloc, and you say, no, malloc, I need 8 kilobytes, or you even say 6 kilobytes. You don't care about pages and so on. What I'm saying is like behind the scenes, so malloc is actually a user primitive, and behind the scenes, the OS has to allocate memory, right? And the way the OS is going to allocate memory is going to do the following, okay, the program needs a stack of, for example, like 10 kilobytes. Well, I need 3 pages because I can only allocate chunks of 4 kilobytes page. It needs, in total, there was a malloc of 6 kilobytes. I'm going to allocate 2 pages of 8 kilobytes. Okay, you don't see it you as a programmer, right? As a programmer, you have only that and so on, but there is more behind the scenes. Okay, does that answer the question?
So once I allocate the space for one program, I cannot use the same pages to add space for another program.
No. If you don't use it, it's gone. That's bad. Here, for example, this small space here, I cannot use it. Because when you when the OS allocates space, it allocates chunks of pages. That's it. But that's acceptable. Actually, this solution is what we're running right now on our OSs and so on. It's better. Okay, interesting question from Alexander Efimov. So you understand the following, right? When you do a bad pointer manipulation or stuff like that, when something goes wrong with your program, most likely it's because you try to read a pieces of memory that is not allocated or is out of the bounds or whatever, right? And usually when that happens in BO9, the program stops and says segmentation fault. Okay, that's kind of the old name in a way, but it means the same thing, right? It's like you try to kind of, you have a pointer that goes outside of what has been allocated to you, right? Maybe the right, and they keep this old word because at some point we're using segmentation, but now we use page. So, maybe they should have upgraded it and say page fault, okay? Actually, Pintos says page fault, okay, because Pintos is recent. But it's the same, okay? Segmentation fault, page fault, okay? Regardless of how you're using behind underneath, okay? Because you can still use segmentation, by the way. Linux still supports it, but, and your x86 machine can be configured in the two modes. But they keep the old kind of expression says segmentation false. It means the same thing. It means that your pointer went crazy, and you are trying to access a piece of memory that you cannot access. Okay, so they still use the same name. Okay. Okay. So pages are fixed size. I told you, right? Usually we use 4 kilobytes. I mean, we're going to use that in PinTOS. Most operating systems use 4 kilobytes. I mean, now actually on Linux, we use 8 kilobytes page, okay? Because now we have bigger memory, we have 64 bits architectures and so on. But usually the default number is usually 4 kilobytes for a 32-bit machine. So it has two parts. Of course, it has the virtual page number, okay? So it's something as segment, right? We're going to divide, when we see a virtual address, we're going to divide it in two. There's going to be a virtual page number. That's going to be the most significant bits, okay? And there's going to be a page offset, okay? That's going to be actually the 12 bits, okay? The last 12 bits. And of course, here it's going to be like, the 21st bit. So 20 bits for the virtual page number, 12 bits for the offset. So what's the page table? It's exactly the same actually as the segment, okay? No, I shouldn't say exactly the same. It's kind of the same idea. For every page allocated, you have an entry in the table, and it's going to say from that virtual page number, here is the physical page number, okay? And we call that VPN, and here we call that physical page number, PPN. I have to tell you right away, you're going to see that in PinTOS, the terminology they don't say virtual, they say page number. When they say page number, it's virtual, but then they say frame number, and that's the physical one, okay? So in PinTOS, they talk about frame. So if you hear frame, it's going to be physical, page is going to be virtual, okay? It's the same. And so on. And plus, it has some bits also in the table. Let me show you. I'm going to show it to you here, okay? So it has some bits. What are those bits? I'm going to talk about these bits again, because you're going to use those bits a lot in project 3, okay? There's going to be a modified bit, okay? So this modified bit, if it's 1, it says that, yes, the page has been modified, okay? So meaning there was a write on this page, okay, in memory. There's going to be a reference bit, okay? Meaning the page has been accessed. So every time the page has been read, it's going to be 1, okay? How we're going to use that? That's going to be very useful for swapping, okay? Actually, the modified bit as well. But this one, we're going to use it for implementing a swap algorithm. There's going to be a valid bit, okay? So same thing, whether the page is actually valid. Same thing, we're going to see that when we talk more in detail about swapping, okay? Some protection also, because we're going to be able to tag a page as either read or write or execute, okay? So if it's a program, we're going to say execute. If it's a read-only page, we're going to put read, and so on and so forth, okay? So it's extra protections. And then, of course, we're going to have the physical page number to know the physical page. Let me show you on this. So here, it looks like exactly the same as segment. It is kind of the same, right? So here, once you have an address, I told you, right? The 21st bit is going to tell you, it's going to tell the MMU. It's going to tell the MMU which index in the page table. So the MMU is configured with the page table, and it's going to look at 3, for example, okay? 3, 0, 1, 2, 3. That's what we call the page table entry. So now, okay, now we have the page table entry, and the page table entry, it has a bunch of bits. Let's ignore for now, but there is no base and bound anymore. That's the difference with segmentation. Once we have the entry, we know right away, that's the most important here, it says, oh, page 3 corresponds to the physical frame, page 5. And so here, now you push the 5, and now you have your physical address. No, it's simple, right? Here, now, that's the virtual one. You need to replace this one with the entry that you have in the page table, replace it with 5, and now you have your physical address. And that's easy as that. And of course, the offset doesn't change, right? So here, it's kind of like, this idea. Let me go back a little bit. This, right? If that's a virtual, you're going to say, oh, it's an address that is inside page 2. I'm going to have some kind of a translation here, which is going to be per process again. Oh, page 2 corresponds to page 1 in the physical address. Okay. And again, this is going to be a translation per process. So each process will have its own page table. Okay. So meaning, actually, you can have 3 processes that use page 3, for example, but those page 3 are going to map different physical page. Okay. Maybe the page 3 of program A is going to be on page 5, but page 3 of program B is going to be on page 13. Okay. And of course, when you do context switch, you need to tell the MMU, here's where the page table is. And right now, if you're curious, actually, if you look at Pintos, and when you look at the TCB, the thread control block, there is actually an information called PDE. And this is the pointer that points to the page directory entry, basically the page table. Okay. So it's there. And of course, when you switch context, you need to switch this table, right? Let me answer a question here. Does the offset not have to be checked that is within the size of a page? Not really. I mean, no, you don't need, because here, the offset, remember, right? The offset is on 12 bits. And 2 to the power 12, this is actually, 4 kilobytes. You see why we choose those values, right? It's exactly that. So you don't need even to check. I mean, necessarily, this offset is within that 4 kilobytes block. So 3 is the row number in the page table, correct? Yes. 3 here is the index in the page table. Yes. 5 is the page number of the physical page. Yes. So here in this page table, the MMU is going to read the page table on 3 here, and it's going to look at this and it's going to say, okay, 5, and now it's going to use it for the address. And 128 is the number of bits we go down in the physical memory. Yeah, in a way, I mean, if you say like 5 followed by 0000, it's going to give you like the upper, I mean the upper bound, the upper, I mean the lower bound, and then you add the offset here. It's going to be directly here. Why is the size 4 kilobytes and not 8 or 16? I'm gonna have a slide about that soon. Okay, I'm gonna have a slide about why it's 4 kilobytes. 4 kilobytes has all kind of good properties. Okay, I will show you that. But actually now it's flexible. You can change it. Linux, you can have actually 8 kilobytes. I don't know about 16. I think you can go up to 16. We call that big pages. It's possible, especially for 64 bits architecture. Yeah. But for 32-bit architecture, the best is actually 4 kilobytes, and I'm going to explain why. Okay, in a second, after the break. Okay, let me talk. I'm going to just finish here about paging, and then we have a break. So why Pages better? Why are we using Pages right now? Well, it's easy to allocate memory. You just allocate chunks, and that's it. You don't need to kind of like have segments and so on and so forth. Memory comes for free. It's a free list of fixed size chunk, right? You can say, it's what is free? It's free, page 0 is free, 0, 5, 13, 24. Okay, that's, for example, how you can manage it. Allocating a page is just removing it from the list. Yes, you allocate a page, you remove it from that list. Okay, I mean, this is naive, right? We can do better than a list, and we will talk about that. External fragmentation, not a problem anymore. Okay, you can have a lot of allocate, deallocate, allocate, redeallocate, and so on. You will never have external fragmentation. Okay. Easy to swap out chunks of a program, right? You want to swap things, you want to relocate a page. You take the page, you relocate it somewhere else, you just change it in table, done. Okay. We can use valid bit to detect reference in swap pages. Okay, we're going to talk about those bits again, right? You will see why they are convenient. And the pages are a convenient multiple of the disk block size. That's for swapping. Okay, we'll talk about swapping a bit later. Okay, but paging is a good way to go. What are the limitations? You have internal fragmentation. Okay, because you allocate 4 kilobytes. But again, in average, the fragmentation is going to be 2 kilobytes per segment. I use segment here, but basically per chunks of memory that you allocate. Okay. And it's acceptable. It's actually better. It's a better drawback than the segmentation approach. It requires 2 or more references, which could limit the performances. Okay, you will see. Doing the translation is expensive. We are going to fix that. Okay, and the solution, we're going to use hardware. There's actually in your computer right now, there's a piece of hardware to speed up the translation. Okay, we're going to talk about that. But this is one of the biggest drawbacks here. I don't know if you have made the count, but here's the thing, right? So let's do quick math. We need every program, we have a page table, okay? And I told you every program would see the memory as if it can use the entire memory. So that means here, imagine we have a 32-bit address space, okay? And we have 4 kilobytes pages. How many entries are in the page table? Well, it's simple, right? You take 2 to the power 32, you divide by 4 kilobytes, that's 2 to the power 20 page table entry. That's a lot of page table. Okay, so that means your page table, we have 20 page table, 2 to the power 20 page table entry. For each process, yes, PT is the number of rows, correct, yes. How many bytes per page table entry? We have 4 bytes. So here, 4 bytes times 2 to the power 20, that's 4 megabytes per pages. Per page table, per process, right? Every process, we have 4 megabyte page table. Imagine I have 25 process, only 25, right? 100 megabytes of memory just for the page table. This is huge. Okay, maybe not those days because we have gigabytes of memory, but I mean, my first computer has 16 megabytes of memory, right? I mean, it was not possible. So here, this is not possible. This is actually, it's an insane amount of memory. I mean, 20 process. Imagine my computers right now maybe has 100 processes. Okay, 100 processes. That's 400 megabytes. Okay, just to store the page table. I'm not storing anything useful, right? Just storing the page table. Okay, and yeah, Raz say here 100 megabytes. That's the entire game on my phone, right? So yeah, probably you don't have 100 megabytes of memory. We're talking memory here, not the disk, right? But that's a big problem. Okay, we're gonna fix it. Okay, that's gonna come next. So FYI, and then we're gonna have a break. Your machine, your computer, right now it's an x86 architecture, supports both paging and segmentation. So you can write an OS that use both, right? I mean both, not at the same time, but you can switch. The segment, I told you it's going to be register-based, but pointer and so on. It's going to be linear address, and then page translation happens on linear addresses and so on. So you can choose, right? But most of the modern OS that we have, they use paging because it's more efficient. There are levels of protections also in memory. Okay, I mean this is something we're not going to see, but the segmentation has 4 privilege level. 0 to 3. In paging, we use only the one I told you about, which is either kernel or user. That's it, right? But on segmentation, you can go like you can have you can partition your memory into like privilege access. Okay, that's just detail. Just if you see those kind of things later, but in Pintos, what we're using right now, it's just like user mode, kernel mode, and we have only 2 level of protection. Okay. That's it. Let's take a good break. Let's see. Maybe I'm not going to have time to finish that, but it's okay. At least I'm going to give you enough details so that you can get started with the project. So right now it's 12:20. Let's take a 5-minute break. Okay, I want to have enough time. So we come back at 12:25. All right, and we're back. So, so I give you a brief introduction about paging, but I need to give you a lot more detail. Okay, we need to understand how it works, and we're going to talk about swapping and so on, because that's going to be the topic for project 3. So again, what's the page lookup? So the idea is the following, right? We're going to take so the physical memory is divided into chunks of 4 kilobytes, okay, or at least a fixed size chunks that we call the page, okay. And here, when we have an address, okay, we have a virtual address. We need to translate that virtual address to the physical address. When you say we, it's actually the MMU automatically, okay. And for that, the MMU will know where we have something called the page table. In the page table, okay, in a nutshell, there are bits and so on, but in a nutshell, what it does is as follows. From the virtual address, it's going to take the first 20 bits, and that's going to be the index. And the index is going to give you the entry in the page table. And this page table entry here, we contain the frame, I mean, the physical page number here that will be used now to combine it with, again, the offset here, the same offset. And now we have the physical address. And now the CPU actually can talk to the physical address and so on, right? So that's how it works. That's a page lookup. So we're going to improve this naive approach of paging, okay? One, we're going to use smaller page table because, again, I told you, right? If we implement it like that on a 32-bit architecture, it's going to take us 4 megabytes per page table, okay? Because the page table entries as a page table has 2 to the power 20 entries, okay? So it's too big. It's going to be 4 megabytes of data in total. Again, per table, meaning per process, that's too much, okay? And again, in this page table, we're not storing any kind of relevant data, right? It's just a translation, okay? So that's too much. We're going to speed it up as well, okay? Because doing actually a lookup in a page table and so on, this is not fast, right? I mean, we don't have a good way to do it at the hardware level in a fast way, okay? So we're going to speed it up and have some kind of hardware level to speed up this translation. Also, what we want to do is like, at some point, we want to use more virtual memory than physical memory. Right now, it's not really possible because I told you, right? Every time you allocate a page, well, you allocate it in the physical memory, okay, somewhere. But what if, the programs evolve, they grow, and, we're running out of physical memory? How can we do that? Well, we're going to see that. It's called swapping. And then we're going to see some advanced functionalities, actually, like sharing and stuff like that, okay? So let's start first with the first improvement, which is smaller page table. So smaller because what? Well, here's the problem, right? Again, I'm going to explain it maybe for the third time, but just so that you understand. So right now, for each process, we're going to have one page table. And this page table is going to record from 0 to n. Actually, here, n is going to be 20. No, 2 to the power 20, sorry. We're going to record which page correspond to what, to which page, what virtual page correspond to the physical frame, okay? So here, if we do that, it's going to record 2 to the power 32 divided by 2 to the power 12. That's 4 megabytes per process, okay? And that's too much. That's a big overhead, okay? So we cannot have that. So what's the solution? Or maybe here, let me say it differently. What is the problem? The problem is that the page table is not a sparse data structure. You need to allocate this big array in order, even if you're only using few pages, right? Even if the program is using page 1, page 3, and page 13, you still need to have this large chunk array, right? The data structure is not sparse. That's a problem. So we have to make it sparse. Sorry, where does the 12 come again? That's the size of it's 4 kilobytes. Okay. So here we need to make this more sparse. So here, each process has a page table that maps all page in its address space. That's a problem. It's not a sparse data structure. And the solution is like, we only need to map a portion of that address space that is actually being used. Okay. So how does that work? Well, we, in a way, you have taken probably an algorithm class. What's the way to come up with, I mean, when you have a full data structures and you want to make it sparse, how do you do it? Well, one technique is to use another level of indirection. Okay, and we're going to call that a two-level page table. Okay, let's go through it. So a virtual address has 3 parts. Now we're going to have a master page number. Okay, and again here, so Raz has again a question. Let me cover that. I'm going to go back to the slides and I'm going to explain why what's this number again. Okay. So now the virtual address. So our old virtual address has 2 parts: an offset and an index. Now we're going to have 2 indexes and 1 offset. The first index we're going to call it the master page number. Okay, the index in the master page table that maps to secondary page table. Okay, and then the secondary page number, and then an offset. Maybe here it's better to explain it on a drawing. Okay, so now what we're going to have is we're going to have a master page table. Okay, and this master page table is only going to contain not all the entries, just a few entries. Okay, and here it's going to be only the if I remember correctly, we're going to say that's going to be 12, and we're going to take, I think, 20 and 20. Sorry. 15 and 15, I forgot. Okay, we'll see how many bits. But here, so that's going to be the master page. And the master page will give us the entry, I mean, the index here is going to give us the page frame entry to a secondary page table. And the secondary page table, we're going to take the second index, and that index here is going to give us actually the index in the page. And finally, here, we're going to be able to calculate the offset. Okay. I don't know if you understand here fully. Maybe actually let's see if I can explain it better. Okay, actually, let me go back. The idea is as follows, right? In the past, what we were doing is the following: we took all these bits here, and that was the index of the table. So of course, here we had 20 bits. We need to have a page table that was 2 to the power 20 entries. Okay, that's too big. So instead, what we're doing is the following: we take only a few bits. So here, imagine this is going to be, actually, let me show you. It's going to be 10, yeah. So instead, we're going to take only 10 bits here. So that means here in this table that we call the master page table, now we only have 10 to the power 10 entries. Okay, and so here we take the index, okay, the first 10 bits, and it's going to give you the what we call the page directory entry. And here now this is not going to give us directly the page as before. Now this is going to give you an entry to a secondary page. Okay, so here there's going to be some kind of a number that is going to tell us here's where you should look at for the secondary page. And so now you can imagine the following. Okay? Here we're going to have as many secondary page table as there are entries here. So meaning here we might have 2 to the power 10 secondary page table. And this secondary page table, once we find the right one here, we use the other 10 bits to find the index in this secondary page table. And finally here, what we're getting is the frame index, okay, or the frame number. And now we have the physical address. So you see, it's kind of like 2 levels of indirection. Instead of doing like one big lookup in one table, we do a first lookup in the first table, which is a lot smaller. That gives us the entry for the second table, okay? And now the second table, we use a second index to get the entry. Once we have the entry, we get the frame. Why is this better? Well, here's the thing, right? I told you before, if, maybe go back here, even if we use only a few pages here, you needed to have the right amount. I mean, you need to have the entire page numbers mapped. Now we don't. Now, okay, here, of course, we need to have the 10 to the power 10 page mapped here, okay, or master mapped here, but that's it. If we use only 3 pages, okay, and imagine these 3 pages are on the same secondary page table, you're going to use another secondary page table, and that's it, okay? Or maybe they are on 2 different secondary page table, but okay, fine. You're going to have 1 master page table and then 2 secondary page table, and that's it. Each of them of how many entries? 2 to the power 10. Okay, so suddenly it's a lot more efficient in space. Okay, let me do a rough calculation here. Okay, so how many bits are in the offset? Okay, if we have 4 kilobytes, okay, the offset necessarily is going to be 12 bits. Okay, maybe that was your question actually, Raz. Sorry about that. Okay, so the 12 bits are for the offset. So if we have 32 bits, we have 20 bits left. And the 20 bits left are going to be for the master and the secondary. So what do we choose? We're going to choose to have 10 bits for the master page index. So that means if we have 10 bits, we're going to have in total 1 kilobyte of possible entries. Okay, so 2 to the power 10, which is 1 kilobyte of possible entries. Okay, 1024. So here, that's the master page table. The master page table has to be there. Okay, it must exist. But then we need to have secondary page table, and we're going to create secondary page table only when we have a mapping, right? So we're not going to create them all. We're only going to create it once we have a mapping. And if we have a mapping, we can still have 10 bits again. So that means here we can have, again, 1 kilobyte of possible entries here. And you see here why we choose 4 kilobyte page, 10 plus 10 plus 12 equal 32. Okay, and that's enough to actually address the entire memory here. Okay. Alexander questions, does the secondary page table has a variable size? No, fixed size, 10 bits. Okay, so here it's not sparse again. Well, as soon as you allocate 1 secondary page table, it's not sparse, meaning you need to allocate those 2 to the power 10 number of entries. Okay, but you see it's a lot smaller. Imagine, I mean, let's take the extreme, right? The extreme is as follows. Imagine a program allocates 1 page. In the old version, you need to have your 4 megabytes because you need to have the entire page table. You have no choice. Okay. Now, if you have one process that uses only 1 page, what do you need to allocate? Of course, you need to allocate the master page table. Okay. So the master page table is going to be like 2 to the power 10 multiplied by the number of bits. I forgot how many bits are there, but you know, the bits per entry. I said there was, I forgot, that's in my previous one. Let me go just quickly. How many bits are there? Why did I do calculation? Let me see. No, I do it here or here or here. Yeah. So we say 4 bytes. 4 bytes per page table entry. So here it means that, oops, yeah, I'm going back here. I need 4 bytes, 4 times 2 to the power 10. That's going to be the size of my page table. Okay. And then I need the same thing here. So yeah, do you say basically like 1,000 bytes? No, it's 2 to the power 10. So Raz, no, it's 2 to the power 10 multiplied by 2 to the power 10. That's the number of entries. And then each entry is going to be 4 bytes. So it's 2 to the power 10 multiplied by 4. So that's basically, if you did the math, yeah, it's basically 4 kilos. Okay, 4 kilobytes of data here. And then if you allocate 1 frame, you're going to create this secondary page table here. So now you're going to allocate, 4 kilobytes, 4 kilobytes. Oh, by the way, this is why it's convenient, yeah, of course, because now a page is actually 4 kilobytes, and you can fit a table inside a page. Yeah, I remember that. Okay, so that's why it's very convenient, this number. And so you only need actually 2 pages, 2 times 4 kilobytes, as opposed to the entire table of 4 megabytes. Okay. Yeah, and something important. Yeah, that's why I say that's why it's kind of useful, right? Because if you have 10 bits, that's actually 10 bits. So it's 2 to the power 10 multiplied by 4. That's exactly 4 kilobytes, and that's the size of a page. Yeah, because again, this table has to fit in memory, right? So you are going to basically allocate pages to store that master table. I hope you're all following. It's a bit complicated, but it's kind of clever. It's very clever, right? So here, if I allocate only one page, the total memory I'm going to allocate for managing the memory is going to be 2 pages. One for the master table, one for the secondary, and that's it. Okay. Okay. So how does it work? One thing, so I told you, right, the OS can switch between segmentations or paging. I mean, usually we use paging. This is controlled by a control register CR0, right? So you have to modify CR0 to tell the CPU, hey, I'm using pages or paging or segmentation, okay? But we use segmentation. Then the CR3 points to the page directory, okay? So again, now we have the page directory, this one, that we call the master page table. We call it also page directory. Maybe I should have put it here. And as opposed to the secondary page table. So here we have a pointer, CR3, that is going to point to the page directory. So of course, every time there's context switch, okay, every time the scheduler switch between threads, we need to update the pointer to point to the page directory, sorry, for that process. Okay, and in Pintos, if you look at page activate, it's doing exactly that. The page directory has 1024 page directory entries. Okay, so that's why if each of them is 4 bits, and that's why the page directory can fit into a 4 kilobytes page. Okay, so that's convenient. So each contains a physical address of a page table. Okay. So the page table here, what they call the page table in Pintos, it's the secondary page table. Okay, so they use page directory for the master, page table for the secondary. Okay, so they use a little bit of different wording. And each page table has, again, 10,024 entries. Okay, that's why we have 10 bits for the index. And each of them, of course, is on 4 bytes. So again, we can store each page table inside a page of 4 kilobytes. And cover 4 megabytes of virtual memory. Okay, so that's why, I mean, you can, if you only need like 4 megabytes of contiguous memory, you can only allocate 2 pages, and that's it. Okay, for managing the memory. And each contains a physical address of 4 kilobytes of virtual 4 kilobyte page. Okay. So again, this is another thing that you might have in the Pintos, I think. So that's kind of the idea, right? So the first 10 bits here, this is a directory. So here, this is going to give you the index inside the page directory. Once you have this index, by the way, of course, the CR3 pointer points to the page directory, right? So the MMU, when the MMU has to translate a virtual address, how does it work? Well, first of all, you look at the index here. You look at the CR3 pointers to point to the table, and then does what? A lookup. What's a lookup? It takes that as an index, do some kind of an offset here, and gets the entry. Once it gets the entry, then it gets the address of the secondary page table. But again, here, this table contains, again, 1024 page table entry. Okay. So how do we know the index? Well, again, we take the 10 following bits, so from 21 to 12, and that's going to be my index in my table. Now, once we have the table, now I extract the page number, the physical page number, and now the physical page number, I combine it with the offset to find the address in the physical address. Okay, and that's it. That's how translation works. Do you have any question about that? It's kind of complicated, but again, I want to insist, this is done automatically. You don't have to do this translation. Now, what your job is going to be about is maintaining this page directory here, okay, and maintaining maybe the page table, okay. I mean, this is implemented in Pintos in a naive way. We are going to improve this management here, okay, by doing swapping and stuff like that. So good question. So for part 2 of the project, you're not going to manage it, but you need to know this translation, because at some point you have to go from a user address to a kernel address, okay? So you need to understand that. If you want to get started with that, maybe actually, you know, something good, I'm going to post that on Piazza. Watch right now the video for project 3, okay? Watch it. You don't need to understand everything, but at least I'm going to show you some interesting thing that you can use for project 2. For project 2, the only concern that you have is the following. The address that you, when you do a system call, the process was using its own virtual address. So the pointers that it pushed to the stack are virtual addresses that are valid within the address, so within the user space. That's important. Why? Because when you do a system call, you switch to the kernel mode. And when you switch to the kernel mode, actually, you are using the kernel page directory mapping. So it's a different one. So now, you know, if you want to read the same data, you need to translate the address, the virtual user address, into a virtual kernel address. And to do that, you have to call a function. But you need to, I mean, of course, it's simple, right? It's given to you, but you need to understand when to do it. And if you want to understand when to do it, you have to think about, okay, this address, this pointer, for example, because it's going to be a pointer, right? Who set it up? Is it the user program? Yes, it means it's a user address, virtual address. I need to translate it so that I can read it from the kernel. Okay, and vice versa, by the way. If you do something and so on, and you create some kind of address, you need to translate it and so on. So there's a little bit of gymnastic here. Okay, so you don't need to understand all of that, but at least you need to understand that yes, there is this concept of like each process has its own virtual address space, address mapping. Okay, because of all of that, and you will need to translate the virtual address to virtual address in project 2. So maybe to help you, after this lecture, while this is fresh, watch the video for project 3. Okay, it's already posted, I think. If not, I'm going to do that. It is posted. And again, go back to project 2 and see what you have to do when you read stuff from the stack. What is this address? And if you try to read it and you get a page fault, why? That's because you need to translate it. Okay. All right. Okay, so, and somebody says, yeah, project 3 is going to be juicy. Actually, students, they find it hard. Project 3 is hard, but they find it very interesting. I think, I'm not going to say you have fun, okay? It's hard. But after project 3, you really have a feel of having work on something hard. But when you understand everything and so on, and everything comes together, it's actually a great feeling. Okay, so I think that's why this course is rewarding. It's rewarding to do hard stuff. Okay, so always. Mohamed Rahman, where are page tables stored when programs start using more memory? The page table is stored in memory, meaning that's why what I'm saying, like, you know, here, the fact that this page directory is 1024 entries multiplied by 4 bytes per entry, that's 4 kilobytes. That's exactly the size of a page. This is stored in memory as a page. Okay, so that's why it's in memory. I'm still confused how the secondary page table saves memory. Doesn't secondary page table contains every page anyway? Not so. Again, okay, let me re-explain that. It's important. There is not a single secondary page table. There are many secondary page tables. Maximum, you're going to have 1024 secondary page table maximum. Okay, but that's never the case because you never have a program that allocates the entire memory. But if you had a program that allocates the entire memory, you would have one master page table and then 1024 page secondary page table. Okay, so here, how does it save memory? Because here, okay, you allocate the entire master page table. You have only one, you allocate it entirely. But imagine you allocate only one frame. Now you need to allocate, of course, the master page table, and then you need to allocate the secondary page table here that you need. But you don't need to allocate the others. So here, you're only going to allocate one secondary page table out of 1024. So you're saving 1023. Okay, you're saying okay, but I want to okay from the person who asked the question. Yes, Alexander, you see it? Yeah. So that's how it's saved. It's sparse in a way, right? It's only like, oh, wait, okay, fine. Here, I need a secondary page table. I'm going to do it. But actually here, I'm going to tell you, if you keep allocating pages and pages and pages, you're going to use the same page table. And at some point, when this page table is filled, okay, now you create a second one and so on. But you only create it when you need. And that's going to save a lot of space. Okay. So in a nutshell, in the old way, you need 4 megabytes per process to store the entire page table. Now, at least, when you allocate only one frame, you only need 4 kilobytes for the master, 4 kilobytes for one secondary page table, and that's it. Meaning you need 8 kilobytes as opposed to 4 megabytes. Okay, but of course, if the program allocate more and more, you might allocate more page table and so on. And at some point, yes, it can grow up to 4 megabytes. It can grow to 4 megabytes actually plus 4 kilobytes. Okay, because it's like 1024 times 4 kilobytes plus 4 kilobytes. You might end up there, but only if the program allocate everything. It's extremely rare that a program allocate the entire memory. What does each page frame contains row? Here, again, we have the same, it's going to be the same protection bits and so on. But here, instead of like, here, for example, the page frame, so you're asking for the page frame. Okay, so let me explain. So the page frame contains the exact same thing as I said before, which is the bits. So I explain it here. It contains the protection bits. Okay, I told you the modified, the access bit, the valid bit, and the protection. Okay, again, more detail later because we're going to need that later on. But then it has also the page index, right? So here, there's going to be the page index, and here there's going to be the same protection bits and so on. Instead of having the page index, this is going to point to the address of the secondary page table. Okay. Actually, I'm saying something wrong here. No, this one does not contain the bits. It contains directly the address of the secondary page table because it has to be a 32 bits address. So yes, sorry about that. The master page table, meaning the page directory, what each page table entry, each page directory entry contains is actually the address of the page table. Okay, I think I have it here. Okay, directory entry is the address of that page table, and here the bits are here, and the page index is here. Okay. Okay, I assume everything is fine. Great. Oh, there was a question that I missed from Anton. Oh, wait a second. Where can I find a video? Everything is on the course website. Yes, I created a YouTube channel for Pintos. Anton, so the secondary page table is not per thread. It is. It is per thread. Yeah, everything is per thread. Okay, so every thread will have a different directory entry, and every thread, and of course, and as many page table as needed per thread. Yes. I answered this question again. Okay, I think everything is fine. Okay. Again, if something is not okay, I understand this is hard. Okay, this is, I mean, I find it beautiful, right? It's kind of a, people who come up with this crazy memory management, they are smart. So it's complicated to understand. I'm not going to expect you to understand everything after this lecture. It has to kind of sink in and so on. There will be some tutorial next week about that. Of course, there will be the project and so on. I mean, all of this is going to contribute that you understand, right? But again, if you have questions, let me know. I can probably answer right now. Okay, where was I? Faster translation. Let's see. I have 4 minutes. Should I cover it? I will try. Let's try to cover it, and then if needed, I can repeat next week. So you see here, maybe here I'm going to say the following, right? Translating an address, a virtual address to a physical address, it's expensive. Why? Because you see here, the CPU, even the MMU, what it has to do is the following, right? First, there is a lookup here in this. Okay, imagine we can do this lookup into one cycle. Fine, okay, or a few cycles. It's okay. So we do this lookup. Once this lookup is done, now we need to do a second lookup. And now, only once the second lookup is done, now we can actually compute the physical address. So you see there is like 3 steps. First lookup, second lookup, third lookup. And you cannot parallelize them. You know, you need the address of the first lookup to do the second one. So it's kind of 3 steps. Each of these steps is going to take some number of cycles, but you know, even if it's 1, it's going to be slow. So we need to translate it faster because again, the MMU, I mean, the CPU will have to do that on every instruction almost. Okay, so that's a problem. So we need a faster translation. Okay, so that's exactly what I just say here. Now, expensive in memory for the 2-page table that we have. Okay, it's 2 table lookup and 1 fetch. I haven't talked about 64 bits, by the way. On the 64-bit machine, actually the machine that we're using right now, there is not only like 2 table lookups, there are 4. Okay, because now you have 64 bits, right? So there's 4 table lookup. Again, I'm not going to re-explain. It's exactly the same thing, right? Except that it's longer, but it's the same idea. So that means that, you know, it's slow. So what's the solution? The solution is to use a hardware material that is going to cache that. Why I'm saying caching? Actually, maybe I want to give you I'm not going to finish the slides, but I want to give you the intuition. The intuition is as follows. For example, when you access a buffer, okay, you know, you in C, for example, you do a malloc, you allocate a buffer, and then you kind of grow to the buffer. As you go to the buffer, you can imagine underneath what the CPU is going to do is going to access memory address that are next to each other, right? It's going to be the first maybe 4 bytes, and then it's going to move to the next 4 bytes, and then move to the next 4 bytes, and so on, right? And it's going to do that because, I don't know, it's a for loop that does something. It's kind of useless in a way to do for every time you need to access this buffer item to do the translation. Why? Because most likely they are going to be contiguous in memory, meaning most likely the translation is going to be always the same. So what can we do? Of course, we can cache it. Okay, we're going to say, oh, wait a second, that index and that, of course, I mean, here, if the slots are the same, only the offset is going to be different, right? But those bits are going to be the same, okay? Most likely. Maybe not if you have a large buffer, but still, okay? So if they are the same, why redoing the translation if we have done it once? Can we cache it? And we can say, oh, index 13, index 27, well, I know that the address, the physical frame is actually the frame 32. Well, let's cache it. And that's exactly the idea here of something we call the translation leukocyte buffer. Again, this is hardware. It's you know, hardwired in your motherboard. Okay, it's a special hardware to translate virtual pages into PTEs. Okay, in a single machine cycle, in one cycle, as opposed to, you know, 3, 4, 5 when you have to do the lookup. Okay, It's a four-way fully associative array. Okay, so I mean the buffer has some kind of an array, and it can cache between, it depends of the size, between 32 to 128 page table entry. Okay, because what we want to cache is actually this, right? We want to cache that. Okay, and so the idea here, I mean, maybe I'm going to continue next time, but I'm going to use that here. It's like, first we're going to look in the TLB. If it's already in the TLB, okay, let's do the translation right away. That kind of look like, by the way, this look like a little bit what we have in the bounce and bound, right? One read directly we get the address. Okay, if it's not, okay, fine. If it's not, we're going to do the translation and maybe update the translation look-aside buffer. But if it's contiguous, it's going to be fine. What you should get from that, and again, I'm going to explain next time, is the following, right? The TLB exploits locality. If you are working on addresses that are next to each other, okay, you don't need to do translation. And most of the time, you're going to hit the cache. And in average, what we say is like, what we have measured, 99% of the time, we're going to hit the TLB and not do the translation. Okay, 99% of the time. And that's why it's going to be super efficient. Okay, we have that right now on our computers. Okay, I'm going to stop here. I'm going to start again next time. So again, what to do after this lecture? It's all maybe confusing and so on. Look at the video for project 3 already. Okay, even if you're working on project 2, but in project 2, think about the following: when you get an address of a pointer or something like this is supposed to point to a buffer, ask yourself, in which word this address is true, meaning in which thread this address as this virtual address makes sense. And if you are in the different context, because you are in the kernel, you need to translate it. Okay? Okay, Puya says it's not there on the course site. If it's not, okay, I'm going to post it. I'm going to post it. Okay, but usually it's supposed to be inside. Let's see. I'm just going to go, maybe it's in tutorial. Okay, it's not there. I'm going to post it. You're right. Sorry about that. I'm going to post it and I'm going to make a Piazza post. Okay. Thank you, everyone. Have a good weekend and talk to you next week again. Bye.